In this video, we're going to see how we can do SLAM on our robot. So we're going to use the LiDAR on the robot along with the ROS SLAM toolbox to generate a map of the environment around the robot and then figure out the robot's position within that map. Then in the next video, we're going to be able to reuse that map with the nav2 stack. So it can use the map to figure out where any obstacles are and autonomously navigate a safe path towards a goal. If you're familiar with SLAM, you'll be aware that it comes in many different shapes and forms that use many different sensors, but today we're going to be focusing on grid SLAM with a 2D LiDAR. So I'm going to start with a quick overview of what SLAM is and how it works. Then we'll look at how SLAM integrates into ROS. Then we'll learn about the SLAM toolbox and we'll get that up and going using Gazebo. And then finally, we'll run SLAM on our actual robot. SLAM is an acronym and it stands for Simultaneous Localization and Mapping. So what are localization and mapping? Well, let's start with mapping. Imagine you want to make a map of your street. You've got a phone on you so that you can track your GPS location, and as you walk along the street, you take note of what you see. Orange house on the left, green house on the right, turn the corner, red roof on the right, white fence on the left, and so on. Once you're finished, you'll have a nice little map of your street. Now that you've got your map, you can use it for localization. Let's say your phone battery runs out, so you've got no GPS and you need to figure out where you are. You can see a white fence on your right and a red roof further up on the left. Using the map, you'll be able to pretty accurately pinpoint your location wherever you are. You've found your location in the global coordinate system. You've localized. It's worth pointing out here that localization isn't navigation. Navigation also uses our map, but that's where we're calculating a path to reach an objective, like how do I get to the orange house via the house with the red roof, and planning a safe path to follow through the environment. Advanced navigation may involve dynamically updating the path as new or moving obstacles are detected. We'll be covering navigation in the next tutorial when we look at the nav2 stack. The problem with the approach we just saw is that we needed that GPS on our phone in the first place to make an accurate map. But sometimes we might only have a GPS coordinate for our starting position, or no GPS at all. In that case, we need to do SLAM. We need to simultaneously localize and map. From our starting position, we might be able to see the orange house and the green house. And as we walk, we'll keep an eye on where they are and consequently where we are compared to them. We could also use our stride length to help us with this position estimate. Then, whenever we see a new object, we know where it is because we know where we are, and it all just goes on continuously. Congratulations, we just slammed. And the result may not be as accurate as with a GPS, but it's much better than having no map at all. SLAM comes in many different forms with many different algorithms, but often we can categorize most SLAM methods into one of two categories. There's feature or landmark SLAM and grid SLAM. So what we saw just then, that was feature SLAM. So our features or our landmarks were things like a red roof or a white fence. Grid SLAM, on the other hand, is where we divide the world that we're seeing up into a series of cells, and each cell can either be occupied or unoccupied or somewhere in between. SLAM toolbox that we're going to be using today is a grid map based approach. Before we start using SLAM in ROS though, we need to take a moment to understand some of the coordinate frame conventions. This is some stuff I probably should have covered earlier in the series, but better late than never. So to start off with, we know that the frame attached to our robot is called base link. Up until this point, when we've driven the robot around, we've set our fixed frame in RViz to something called ODOM. In the absence of any other reference, ODOM represents our world origin, and the transform from ODOM to baselink is calculated by the differential drive controller using the wheel odometry. When our robot first starts up, it's at 0, 0. The two frames are on top of each other. As the robot drives around, baselink will move compared to ODOM. Now here's the important bit. The motion of baselink relative to ODOM may not be exactly correct, but it will be smooth. What I mean is, it's possible that you drive the robot forward in real life by 2 meters, but when you check RViz, baselink is only at 1.9 meters ahead of ODOM. This 100 mil error did not suddenly appear. It built up over time as the odometry drifted. You could take any small section of that trajectory and it would be nice and smooth and basically correct, but it just slowly got away from the truth. This is because odometry is effectively a measurement of the robot's velocity, even if it's technically measuring wheel angular position. This velocity is then integrated smoothly over time to produce the position transform estimate. Let's say we now introduce a system that can correct for this drift, like GPS or SLAM. Because these systems directly measure the robot position, If we were to use them to update the ODOM to baselink transform, this could cause the robot to jump around. Now, this might not be a problem, but some algorithms won't like it. Instead, we want to introduce a new frame, the map frame, and we can now express the location of baselink compared to that. So we can have the baselink compared to the ODOM frame, or we can have the baselink compared to the map frame. This gives us a new problem though, which is that a frame in ROS can only have one parent. The way we get around this is that the code will need to take the position estimate from SLAM or GPS or whatever, along with the current ODOM to baselink transform, and calculate the appropriate map to ODOM transform. This is a bit weird since the map to ODOM transform is kind of meaningless out of context, but it means that we can get the baselink pose relative to either reference point with no troubles. And it should move smoothly but drift compared to ODOM, and jump around but stay generally correct over time compared to map. As well as the ODOM and map frames, you'll also find ODOM and map topics, which contain the data about the odometry and the map. The ODOM topic contains basically the same position information as the ODOM to baselink transform, but it also contains the current velocity and the associated covariances. The map topic contains the actual occupancy data for the grid map so that it can be shared to other nodes, and we'll be using this one later in this tutorial. One other thing to be aware of is that in addition to the baselink frame, some SLAM systems also like you to have a base footprint frame. And that's because some robots can move up and down in 3D. The baselink will move up around in Z. But we want to treat the SLAM problem in this case as a 2D SLAM problem. So the base footprint frame is kind of like the shadow of the baselink frame on the ground. So it's stuck to the XY plane, Z equals 0, it's stuck on the ground, and it'll move around underneath the baselink and be used for SLAM. One last note on phrasing, I'll sometimes use the word pose, which refers to the robot's position, its location, and its orientation, what angle it's at. And pose is pretty much equivalent to the robot's transform frame. All of this coordinate frame stuff can be super confusing, and hopefully it'll start to make a little bit more sense once we put it into practice on our robot. If you do want to find out more about it, you can find it in the ROS standards, particularly Rep 105, and also a little bit in Rep 120. For this tutorial, we're going to be using the fantastic SLAM Toolbox package by Steve Masensky. Now, Steve has contributed a number of great packages to the ROS2 ecosystem, particularly SLAM Toolbox and also Nav2 that we'll be looking at in the next video. Before we install it though, I'm going to go ahead and add an extra link to our robot URDF, and that's that base footprint. This one. That's the base footprint that I talked about just before. So if we go up to here to our base link, I'm just going to add it here just under the base link. I've already got it copied, and we can see it's the base footprint link. The name is just base footprint, and it's attached to the base link rigidly with no offsets or anything. So it's going to be just sitting exactly on top of the base link because our robot is just sitting on the ground anyway. So I'm going to save that, and then I'm going to go ahead and install SLAM Toolbox. So sudo apt install ROS Foxy SLAM Toolbox. SLAM Toolbox has a few different modes that it can run in and a lot of different options. Now, the mode that we're going to be using today is called online asynchronous. So online means we're running it live rather than running it through some previously logged data. And asynchronous means that we don't care about processing absolutely every scan. Instead, say that our processing rate is a bit slower than the scan rate, we just always want to be processing the latest scan, even if that means we miss one occasionally. Now, to make things a bit easier for us, SLAM Toolbox comes with some launch files and params files that help us set the options. So I'm going to take one of those params files and actually copy it into our local directory. So I'm going to copy /opt/ross/foxy/share/SLAM Toolbox/config. And now you can see there's a few different options here. I want mapper params online async, and I'm going to copy them into my workspace, into my config directory. And now if we swap back to VS Code and look in our config directory, we can see the file here. So this should be all the parameters that we might want to change for SLAM Toolbox. Now, it looks pretty scary. We're actually only going to change a couple of these in this video, but the rest are there for you to play around with and see how it works. And to start off with, we're going to be running in mapping mode like we see here. And we can see that it's going to use the ODOM frame as ODOM, the map frame as map, and the base frame as base footprint, and the scanner topic as scan. So everything as we've already got it set up. So I'm going to hop into our workspace. I'm just going to build it with Colcon just in case anything's changed. I'm going to source the workspace and I'm going to launch our simulation. And I'll also launch RViz. We should see our robot come up like normal. And if I just drive it around for a little bit, and what I'm going to do is here in Gazebo, I'm going to try and come straight back onto the origin. And what we'll probably find in RViz is that I'm actually shifted a bit from where I started. Now, to be honest, that's pretty good. I've actually ended up quite close. Maybe our gazebo odometry is a bit better than it would be in real life. But usually you'd find that the robot at this point has drifted away a little bit from where you started. So what I'm going to do now is I'm going to restart the gazebo simulation to put our robot back at the origin. I'm restarting RViz as well. You really shouldn't need to, but I find that sometimes it just plays up and gets stuck in a bit of a state. So we'll rerun it all. All right, there's our robot back at the origin. And now what I'm going to do in a new tab, I'm going to type ROS2 launch SLAM toolbox. And we can see what launch files we've got here. And we want online async.launch.py. We'll specify the params file. So that's a parameter for this launch file. And that'll be source/articubot1 config mapper params online async. And then we can also set use sim time to true, and that should pass it down to everything underneath. So that should be running SLAM now. And what we can do back in RViz is we're going to add a map. I'm going to set the topic to /map. And hopefully what we'll see is our map appears. So this is the area around the robot and the rays that it's casting. Now I'm going to go ahead and change the fixed frame to the map frame. And what that's going to mean is that the robot can jump around and the map is going to stay steady. If I left it at ODOM, the robot would be moving smoothly, but sometimes the map could jump around. It's the same thing, it's just a matter of perspective. So now with the map frame fixed, I can start driving the robot around, and we'll see that as we drive it around, it starts to generate a map of what it's seeing. And you can go ahead and tweak the parameters in the config file to change this. As I move out of bounds, it should just grow the map to contain the new area that I'm in. And sometimes it might look like things are a little bit off. And this is where it helps to swap your RViz view to top-down orthographic. So this is a 2D view. I can't rotate in 3D anymore, but we should find that everything stays in roughly the right spot with no perspective errors. And so if I keep driving and get back to the origin now, what we'll see is that if I get back to the map origin, which is here, I'd expect to be very close to my origin in Gazebo. But if we open up the transform tree and show the names, you can see that the ODOM frame has drifted a little bit. So that distance there, which is, I don't know, maybe 200 mil that way, 400 mil that way, that's how much the ODOM has drifted compared to the ground truth. And we've used the map to keep us locked in to where the robot really is. Once we've made that map, we might want to save it to use in the future. Now, if I open a new tab and write ROS2 service list, we should see that SLAM Toolbox offers us a whole bunch of services for things like saving map and serializing map. But to make that a little bit easier, it also comes with an RViz plugin. So we can go add new panel, SLAM Toolbox plugin, and we see all these options here, and in particular the save map and serialize map buttons. Now, this is really confusing, but as I understand it, save map is to kind of save in the old format that maps used. So you want to do that if you want to pass it into some kind of external system that's using the map. Serializing the map is if you want to save it to reuse with SLAM Toolbox, either to localize with it or say you want to modify the map in the future. So I'm going to actually save in both formats, and I'm going to call it my map save and my map serial. There's nothing wrong with giving them the same name because they'll have different file extensions. I'm just doing it to make it clear for the tutorial. So I hit save map and then serialize map, and there's no kind of prompt or anything. But if I open up the file browser and go into our workspace, we can see here we've got mymapsave.pgm, and look at that, we even get a little preview of the map there. Mymapsave.yaml, so that's the old format. And then the serialized ones is .data and .postgraph. Now that we've saved our map, we can try to reuse it for localization. But first, I'm actually just going to clear the map so that we can see that it is actually loading it and not just keeping it open from before. So I've just rerun SLAM Toolbox, and if we give it a moment, this should clear. All right, so I've just rerun it and cleared the map so that you can see that it's all been reset. So we're going to go back into our parameters now. We're going to change mapping to be localization. For the map file name, I'm going to write the path to our file, but without the extension. So it's this my map serial one. So it'll be /home. It'll be /home/dev/devws/my map serial. And then I'm going to tell it to start at doc. So I think that's telling it to start at what's called the first node of the pose graph. What that should mean is that it's starting at the same place that you started when you made the map the first time. You can also use the start pose to specify a specific pose in space to do it. But we're going to go start at doc, localization. All right, all that looks good. So now I'm going to rerun SLAM Toolbox. And you can see it's preloaded back up our old map. And if I drive around, we should be localizing just like we were before. So you can see the ODOM frame there that's jumping around a little bit. Our robot would also be subtly jumping, but it's hard to tell. And I can start driving around. If I start driving a bit faster, we should see the jumps a little bit more obviously. Now, the odd thing you will notice is that we do seem to sometimes be creating new maps. At first, I thought this was just kind of part of how the pose graph based system works. But the more I looked at it, the more it seemed to actually be doing mapping. So I'm not 100% sure what's going on there. But the point is that we can reload an old map and localize against it. Once we've generated our map with SLAM Toolbox, we can actually use that map with other localization systems, which might be better for different situations. One of those systems that's particularly popular is AMCL, which stands for Adaptive Monte Carlo Localization. Now, the standard ROS2 implementation of AMCL is actually part of the nav2 stack. So even though we're going to really be doing a deep dive on nav2 in the next video, I'm going to go ahead and install it now. So here's the command for installing nav2. I've just copied and pasted this straight from their Getting Started guide. Note that if you're on Humble, the command is slightly different, and you probably don't need the Turtlebot 3 stuff to start with, but if you're going to go ahead and do the nav2 tutorials, it's going to be helpful. So I'm going to go ahead and install that. Actually running the nav2 AMCL is a little bit clunky, and so it comes with a launch file, which is very helpful. And we're going to use that in the next video, but this time we're going to do things a long way. It's a little bit more difficult, but it'll help us to understand things a bit better. So the first step of this is that we're going to run a map server. So that's a node that's going to take that map file that we've saved and make that available on the map topic. So to run that, I'm going to type ROS2 run nav2 map server. And we want to run the map server node. Now we've got some arguments for this. So the first argument is going to be the YAML file name. And that's going to be the path to the map YAML file. Now it's actually in the current directory we're in. So I think it was mymapsave.yaml. So remember, we're wanting the one that was saved rather than serialized because it's going to an external system rather than SLAM Toolbox. And of course, our other parameter is just going to be use sem time. And we'll set that to true. So we'll run that and nothing's happening. If we have a look here, it says map server lifecycle node launched, waiting on external lifecycle transitions to activate. So we actually need to run something else to activate this node. It's kind of waiting in limbo. So I'm going to open up a new tab and type ROS2 run nav2 util lifecycle bring up, and the one I want to start is the map server. So if we go back to that, you can see it's found the image file, which was that PGM. So it's loaded the YAML. The YAML's told it where to find the PGM. It's read the map, and it is now publishing it on the map topic. After then rerunning RViz and Gazebo, we should see that our map is now loaded up. Now, we don't know where our robot is anymore. There's no localization running, so as long as our fixed frame is on map, we should see this. Sometimes it doesn't show up properly. You might have to reset or turn the map on and off. Sometimes, like we see here, it's not showing up. We need to change the durability policy to transient local. Sometimes it just works anyway, I'm not sure, but it should be reliable and transient local. And so, yep, we can see our map there, it's loaded up. The next thing we want to run is amcl to localize our robot against the map. So I'm going to open up a new tab and we're going to type ROS2 run nav2 amcl, amcl. And again, the only argument that we're going to provide this time is use sim time. Now, what I'm actually going to do, I'm going to go into Gazebo, and I'm going to drive the robot around a little bit, just put it somewhere slightly different. So, it's just up here. So again, you can see amcl is now waiting to be launched with the lifecycle thing. So this time we're going to run lifecycle bring up on amcl. Nothing happens yet. If we go back to this, we'll see it's subscribed to the map topic, it's found the map, it says it cannot publish a pose or update the transform. Please set the initial pose. So we need to give amcl a suggestion of where the robot is to start with. Now, if you recall, it should be somewhere around here. So we're going to click the 2D pose estimate button in RViz. Make sure we're in the map frame and we can see our map. I'm going to click and hold and then drag in the direction the robot is facing. So it should be like that. And you can see amcl thought for a second and then found the robot. You might notice it printed this failed to transform initial pose issue. That can cause problems sometimes, but for now we're just going to roll with it. So you can see it's found where we are. It's got things a little bit wrong, but if we keep driving around, what we'll generally find is that it should stay roughly correct. Obviously we're not generating new maps, so I can't go too far out of bounds. But if I go around, I should be able to do some, pretty crazy things, and amcl tends to be pretty stable at getting it back to where it is. It might not stay perfectly accurate exactly where it should be, but you can see our odometry has now drifted way off, and yet amcl has us located fairly well. You can probably change some of the settings and stuff for amcl and really dial it in and get it working quite good, but this is pretty good for now. Instead, we're going to head to something more exciting, and that's to run SLAM Toolbox on our actual robot. All right, I've moved things inside the house to give us a bit more space. And to start off with, I'm just going to run the same control launch file that we've been using on the robot in previous videos. So I've launched that here, and once that's up and running, we should see our ODOM in RViz. There we go. Then in another tab, we'll run the RP LiDAR driver. And then once that's up and going, we should see our LiDAR data as well. So hopefully we can get a bit of a sense of the room around the robot. So in RViz, I've got the fixed frame set to ODOM at the moment. And now I'm going to swap to the dev machine and run SLAM Toolbox. Now this is exactly the same as we were running it for Gazebo, but this time we've got sim time set to false. So with that running, we can enable our map in RViz. Just give it a second to make the map. There we go. And now we can change the fixed frame back to map so that our map stays still while the robot moves around. One problem that we can run into if we're running SLAM Toolbox on the dev machine, but the LiDAR driver on the Pi itself, is issues with transmitting that LiDAR data over the Wi-Fi. So in this case, I'm going to be getting packet drops and latency issues, and you can see in RViz that the LiDAR data seems to kind of freeze up and jump around, and SLAM Toolbox is going to be having to deal with those same issues. But you can see there, the map actually looks pretty good. SLAM Toolbox is quite robust and it's able to deal with that jumping around. If that is a problem though, we can of course run SLAM Toolbox on the robot itself. If you're going to do that, you want to make sure that the processor on the robot is capable of handling it. So it's probably going to be pushing the limits for the Pi. For a small room like this, it might be all right, but you wouldn't want to push it too hard. What we're seeing here is really only the very tip of the iceberg when it comes to SLAM and mapping and localization. There's so much more we can do with different sensors like 3D LiDARs and cameras and IMUs and different algorithms. So if that's something that you want to know more about, then Let us know in the comments, and maybe we can do more videos in the future covering different algorithms and deep dive into some of the crazy maths behind it all. So I want to give a big shout out to Steve and to everybody else involved in the creation of SLAM Toolbox. It's so great having a tool that just makes it so easy to get up and going with SLAM and mapping and localization and that sort of thing. So have a go at playing around with some of the different parameters, maybe start by changing the grid size, and then in the next video, we're going to see how we can use our map to navigate using Nav2. As always, thanks so much to the patrons over at Patreon who make these videos possible. If you've got any questions or comments about the things that happen in this video, you can check out the link to the discussion thread down in the description, and you'll also find links to the Patreon page and other good stuff down there. All right, I'll catch you later.